5 minutes later. Okay, I don't want to give these all away, but let's at least figure out what the 72 divided by 360 is. Hey Google, what is 72 divided by 360?
72 divided by 360 is 0.2.
0.2, that's not a fraction. But it's 2/10, and 2/10 equals 1/5. Ta-da! What is our learning focus for today? Find patterns of line and rotational symmetry in regular polygons. That's funny they call it line symmetry instead of reflective symmetry. What makes a polygon regular or symmetric? How does the symmetry of regular polygons differ depending on the number of sides? You can read the last one. And here we go. A line that reflects a figure onto itself is called a line of symmetry. A figure that can be carried onto itself by rotation is said to have rotational symmetry. A diagonal of a polygon is any line segment that connects non-consecutive vertices of the polygon. So the diagonals may or may not be lines of symmetry. This is a separate concept, two different concepts. Lines of symmetry, diagonals of polygons. Sometimes they overlap, sometimes they're the same thing, sometimes not. For each of the following regular polygons, describe the rotations and reflections that carry it onto itself. Be as specific as possible in your description, such as specifying the angle of rotation. Well, for the triangle, we have if we reflect this over this line, it'll reflect back onto itself, which makes it a line of symmetry. Oh, my triangle's weak. What's wrong? Is this paper faulty? Come on. Okay, well, whatever. It flipped. I'll flip it back. Ready for the dramatic flip? Flip. Get on there. Ah, earthquake. Okay, so that's a line of symmetry. And let's look at this line of symmetry. It goes through a vertex, and the midpoint of another side. That makes sense because there's 3 sides. So 2 sides have to land on each other. The third side needs to split in half and land back on itself. And interestingly, there's 3 of those. There's 3 of those lines that go through a vertex and the midpoint of the opposite side. Okay, also if we start, so 3 lines of symmetry through a vertex and midpoint of opposite side. Okay, let's rotate. 1, 2, 3. Let's say I don't know how much rotation that is. I'm going to use this faulty paper again. How much rotation is that? Looks like more than 90 because the top of this is horizontal, top of this patty paper. But when I turn it, like that would be 90 when the next one's horizontal, but it's more than 90. But we can easily figure it out. It's 360 degrees total divided by 3 rotations, and that equals 120 degrees. How about a square? What's going on with our square? Well, we've done the square, and we did it in the last lesson. So we know we can reflect over these. We have symmetries. We can fold over. Or not really fold. It flips around, or it reflects, right? Let's look at this line of symmetry, this line of reflection. Points will reflect perpendicularly, so they'll actually travel along the side and go equally distant. So as long as it's in the middle, the midpoint of the side, it'll travel down and land on itself. So it'll travel down and land on itself. This whole side will travel perpendicular and land on where the other one is, and so forth. So that's line of reflection. That's the line of reflection. But also, same logic going through double corners, double vertex. So 4 lines of symmetry. 2 through mid P of opposite sides, midpoints of opposite sides, 2 through opposite vertices, corners. 1, 2, 3, 4 rotations, 360 divided by 4. Knock off the 0. 36 divided by 4. 9. Put the 0 back on. And here's something. It's 90, 180, because you can do another 90, 270. And the 360 doesn't count for rotational symmetry, but I like thinking of it because then it would make 4 total. We divided by 4. That's the 4th one, even though 360 rotation doesn't count as rotational symmetry. So maybe I'll write in parentheses. Same thing here. This is 120 and 240. Okay. I see this one, but you know what? Through this corner and this midpoint, that would, sometimes people have to rotate their paper to see it, because our minds easily calculate side-to-side symmetry. It's harder to calculate symmetry at some weird angle like this. But you can see the logic. This stuff would reflect over and land on this other arm. These would reflect over and land on this arm. And this odd-numbered side, this 5th side, reflects onto its other half. So that's 1, 2, 3. We have a corner here. Did I miss any? 1, 2, 3, 4. Oh yeah, this corner, this midpoint. So 5. Pentagon has 5 sides, and we have 5 lines of symmetry. All go through a vertex and the mid P of the opposite side. How about rotational symmetry? Ding, 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 ding. 360 divided by 5. You can't divide 360 by 5. Yes, you can. No, you can't. Yes, you can. Maybe. Can you? Hey, Google.
I can't connect to the Wi-Fi network.
Okay, geez. What is 360 divided by 5?
360 divided by 5 is 72.
Ooh, 72. And then all multiples of 72. Now, at some point, we should, back with instructions, specify the angle of rotation. Well, okay, so I guess let's list them for now. 144. Ooh, that's fun. So we won't always have to list them, but since this is the first time we're doing it, let's list them. What are the multiples of 72? What's that times 3?
72 times 3 is 216.
And let's see if we can add 72 to this. 282, 288. Okay, and that makes sense. If we add it again, it'll be 360. And that's 5 rotations. Okay, I think you have enough information to now complete the hexagon, the octagon. Hey, they skipped the septagon, but they went to the nonagon, which is a 9-sider, on the next page. Then make an observation about the lines of symmetry. And, okay, hint there, the even numbered sides versus odd number sides, they behave slightly differently. Look back at your lists and at the types of lines, and talk about the lists of rotational symmetries based on the number of sides of the regular polygon. Okay. After you finish doing the hexagon, octagon, and nonagon, and answering these two questions, there'll be a third video where we go over the takeaways. All right, have fun.